We can make less questions.
My name is I'll chair this session. The first speaker in this session would be Eli Zeldov, and he'll talk about superparamagnetism and quantum anomalous Hall effect.
Okay, thank you. So indeed, the talk will be about the quantum anomalous Hall effect and superparamagnetism in magnetic topological insulators. The work was done in a group at our group at Weizmann. Most of the work was done by Eli Zeldov, who is here. You can ask her questions later, together with Andrea Young, who is currently at UC Santa Barbara, in collaboration with the group of Nitin Samarath from Penn State and Martin Huber from University of Colorado. Okay, so actually the quantum anomalous Hall is a close cousin of the quantum Hall effect. And in order to achieve a quantum Hall, there are essentially three main requirements. One is that we have to break the time reversal symmetry. And in the usual quantum Hall, it is done by applying a magnetic field. The second is that we need a bulk gap. And in this case, it is achieved by Landau levels and the gap between the Landau levels. And the third requirement is to have a gapless chiral edge states. And this is achieved by the hopping orbitals, where the Landau levels cross the Fermi energy. But this is not the only possible way to achieve quantum Hall. Alternatively, you can break the time reversal symmetry by long-range ferromagnetic order, which is the hallmark of the quantum anomalous Hall state. You can open a bulk gap just by using a topological insulator. And in this case, you automatically get topologically protected surface states. So if we look into this possibility more closely, the idea is that you start with a 3D topological insulator film. It has a bulk gap with inverted bands and the surface states. Then if you have a long-range ferromagnetic order, you will open a gap in the surface states. And if you tune your Fermi energy into this gap, then you have gap in the bulk, you have gap in the top and bottom surfaces, and you end up with edge states at the edges of your film. So this is the theoretical recipe for achieving the quantum anomalous Hall state. And indeed, very recently, as we have heard from Professor Q, it was achieved. And this is their data in chromium doped bismuth antimony telluride thin films. So what you see here is the rho xy as a function of magnetic field for different values of the back gate, namely for different levels, for different positions of the Fermi energy. So when the Fermi energy is in the conduction band or in the valence band, you have essentially regular anomalous Hall effect. This is your coercive field due to the ferromagnet. And the value of the rho xy that you get is proportional to the carrier, or inversely proportional to the carrier concentration and the magnetization. But when you bring your Fermi energy into the gap, you reach the anomalous quantum Hall plateau. This is a quanta in h over e square. And you need quite low temperatures in order to achieve that. So now if we go back to the quantum Hall and the quantum anomalous Hall, there are several important differences. So first is in the quantum Hall, one can achieve a lot of plateaus with different new values. In the quantum anomalous, so far only nu equal 1 state has been observed, and there are some reports, as we heard, about nu equals 0. But essentially, it is nu equal 1 and nu equals -1 state. The second important difference is that the quantum Hall is an equilibrium state. It's a thermodynamic state. This is a metastable state. This hysteresis arises from the metastability of the ferromagnetic state. And even the fact that we have a quantum anomalous Hall at zero magnetic field, which is the main interesting part here, arises from the fact that it is metastable. So we can magnetize the ferromagnet entirely at high field, and then when we come back to zero field, it remains fully magnetized, and it actually remains magnetized when you go even to the negative field, namely you are in a metastable state. The third important difference, which I'll mainly focus on, is the source of the physics of the Plateau transition. So in the quantum Hall state, the source, or the way we describe the Plateau transition, is that when the Landau level crosses your Fermi energy, due to quench disorder, you form islands with different new filling factors. And around these islands, you have edge states, which allow you tunneling, essentially, from one edge state to the other. And this gives rise to this large dissipation in the transition region. Here, in this case, we have no Landau levels. Essentially, nothing happens to the electronic state to first approximation as you change the magnetic field. And the reason that you have this Plateau transition here is because this is the coercive field of your magnetic signal, of your magnetic system. So in this picture, you imagine ferromagnetic domains pointing in the opposite directions at the transition. And the interface between the different domains gives you edge states, so you are back similar to this state. But the disorder is not a quench disorder. This is a dynamic disorder of your magnetic system, which induces this Plateau transition. So in essence, here you have a quantum phase transition of the electronic system in presence of disorder, whereas here you have two coupled quantum phase transitions. One is the magnetic phase transition, and this phase transition drives the electronic phase transition. So what I'll be focusing in the rest of the talk is try to understand this coupling between the magnetic system and the electronic system and the nature of this ferromagnetic transition here. So our technique are squids on tip, as was previously by Yoni, was briefly discussed. So essentially, we take a quartz pipette, we deposit a superconductor on each side, making two leads, and we coat the apex ring. As a result, we have a very small squid residing on the apex of a very sharp pipette, which is ideally suited for scanning probe microscopy. And we can use any of these superconductors to make the devices. This is, for example, a LED squid on tip. Maybe we can dim a little bit the lights. They can do it from remotely. Thank you. Oh, much better. So these are the two superconducting leads. This is the ring. And these are the quantum interference patterns in these devices. This particular device has a diameter of 160 nanometers. And what is particularly interesting about these devices is that they're extremely sensitive to spins. And this device has a spin noise of 1.4 Bohr magneton per square root hertz. We can go to smaller devices. This is a 46 nanometer, and it has a spin noise of about a third Bohr magneton per square root hertz, which means that in principle, we have enough sensitivity to measure the magnetic field arising from a single electron spin. So we have two microscopes, one that works at 4 Kelvin, one that works at 250 millikelvin. So this is, we have studied this chromium-doped bismuth antimonide telluride film, which at lower temperature shows the quantum anomalous Hall state. What you see here is the scratch film. And this barely you can see here, this is our squid on tip, and this is its reflection. So if we do transport in situ on this device, we see a very nice anomalous Hall effect. It's quite close to quantization, not quite. But if you go to lower temperatures, these samples show full quantization. This is the corresponding RxX. And now we image the magnetic structure, let's say at this point, close to the coercive field. So what you see, what you see is the distribution of the magnetic field on the surface of the film. This is 1 micron scale. Red domains show stray field pointing out. Namely, we have a domain that is magnetized out. And blue regions are domains that are magnetized down. So indeed, this is what we expect from a ferromagnet. Maybe usually we would expect larger domains, but these are quite small domains. But this is what naively you expect from a ferromagnet near the coercive field. Now if we look at the diagonal point here, just coming back, you see a very similar picture. And if you look closely, you see that it's essentially identical, just the colors inverted. So for example, here you have blue, red, blue. Here you see red, blue, red. This is a little puzzling because if it would be a ferromagnetic film, you have domain structures. As you sweep the magnetic field, you don't have to go through exactly the same sequence. But now we look at the fully magnetized state, which we expect it to be long-range ferromagnetic state, uniform, in which case we would see nothing. But you see that actually it is highly inhomogeneous, quite similar to this. It's about half the signal, but still very far from a long-range ferromagnetic order, as we would expect. If we go to the opposite point, we see very similar picture. And again, it's essentially the same, just the colors inverted. Blue here, red here, and the opposite. So now, in order to see what actually happens, I'll show you a movie. As we go along this magnetization curve, we'll sweep the field and see what happens. Yes?
If you know, but is it known whether this is a block or nail type of wall in the domains?
Good question. I don't think it's known. We cannot tell.
Which way are you applying the field?
Excuse me?
In which direction is the field being applied?
Okay, so now I'll increase the field from 140 to 156 millitesla in 1 millitesla step, going into the red direction. Okay? So this is the starting point. Now that we increase the field, in a ferromagnet we expect the red domains to expand, the blue domains to shrink, and we should see a domain wall moving across the sample between these, or many domains as we see. So now I'll run the movie, and all that you see looks like noise, just flickering, no domain motion, no expansion of red domains and shrinking of blue domains, just some flickering around. So now in order to understand better what we see is I'll show you images which are differential images, namely this image minus the previous one. So now we look only at the differences, what happened since by increasing the field by 1 millitesla. So blue color here shows that nothing happened. So in the blue regions, there was no change. Red means that there is a small domain that was pointing downwards, and now it is pointing upwards. So the blue peaks means that there are some small domains that have flipped from negative to positive direction. Now I'll run the movie again. Look at these domains. They appear randomly in space. Their characteristic scale is about 100, 200 nanometers, which is comparable to the size of our squid. And they're all pointing upwards. Yes?
Suppose you didn't. Suppose it was a very large ferromagnet. You come with a squid.
You would see zero.
A very large but atomically thin ferromagnet, and you come down with a squid.
You would see nothing.
Exactly.
Yes. So it means that it's not uniform magnetization. So it means that you locally are highly non-uniform.
No, but why? I mean, but at the same time, this is a bulk magnet.
No, this is thin film. This is 7 quantupole layers, thin film.
But this could still be that. What I'm basically asking is whether those bad regions are coming from the bulk, but basically the surface, which is the important part for the quantum anomalous Hall effect, is actually as perfect as these blue regions.
Could be. So to answer Aaron's question, we don't have the resolution to know what happens within the thickness of the film. So we basically integrate the stray field from the entire thickness of the film. Absolutely correct.
But you can you absolutely calibrate the
Yes.
magnetic moment?
Yes, I'll show you.
Compare that with what you get from bulk magnets?
Yes, and if we integrate all these events, it compares to the total magnetization, consistent with the total magnetization that you can measure. Yes. But I'll okay. So so now we can do some statistics on these events. So these are the locations of these events. And as you can see, it's randomly, it occurs randomly. Now we can do another thing. We can prepare our system in a given state, let's say here, and then do nothing. Just stop there. So increase the field or bring the field, let's say, to this point, and just wait and just take images every 5 minutes and see what happens. So again, I'll show you an image of that, a movie of this. So these are just, nothing happens. Just every 5 minutes, we take an image, and we see exactly the same thing. So there is slow relaxation as a function of time, and these small islands just flip with time in the direction of the magnetic field. Okay, so we have a tilted potential, and they occasionally hop down to the lower state.
Do they appear in the same places as they did before?
Okay, so this is very hard to tell. You have to prepare it's all metastable, so they all flip downhill. So in order to see them again, you have to prepare your state again, and then to repeat it. So to bare eye, it looks the same. To do the whole statistics again, we haven't done it carefully to tell that it's exactly the same place.
Because I'm asking, do they correlate with the locations of the chromium atoms?
Well, we don't have atomic scale resolution. Okay, but I'll come back to this in a second. So now we can do, again, statistics. We can, each event we can quantize, and we know exactly what is the magnetic moment of each flipping island. So it's typically a few times 10 to the 4 Bohr magneton. Knowing our chromium concentration and 3 Bohr magneton per chromium, we can translate it into physical size, assuming that it's uniform over the entire thickness. If we assume that it's on the surface, it will be much larger, and this would be inconsistent with our. So what we see that their characteristic diameter is about 50 nanometers, somewhat smaller than our squid diameter. In this particular case, it was, I believe, 150 nanometers. So for us, they look as point dipoles, essentially. And this is the statistics when we're here. When we get closer to the coercive field, we actually see that the distribution is broadened. We can get up to a few times to 10 to the 5 Bohr magneton, but the characteristic size is still below 100 nanometers. So essentially what we see that we have, instead of having a long-range ferromagnetic order, we essentially have superparamagnetic particles below their blocking temperature. So they weakly interact with each other. Each of them has its own coercive field. They flip independently. They weakly interact with each other. And they are the ones that are responsible for this Plateau transition. They trigger the electronic phase transition. So we have a magnetic system that actually drives the electronic system. The question is whether electronic system can drive backwards or can influence back the magnetic system. So this brings us actually to the question, what is the origin of the ferromagnetism in the first place? So these are essentially very dilute.
If the structure is so dense, why do you get quantization?
Perfect. That's the million-dollar question. Yes. Yes, absolutely.
Along this line of this question,
yes.
The span of magnetization you saw was 0.1 millitesla. 0.1 millitesla as compared to 130 millitesla, right? That you apply.
No, but this is what we apply has no meaning. You're meaning this. So these changes are about they're very small relative to this. So by eye, you hardly see the difference. Right. If this is what you mean. Yes.
But the electrons feel the sum of both fields, right?
Yes, but the exchange is much larger than the applied magnetic field. So the applied magnetic field for electrons at these fields, this is 0.1 Tesla. So this is negligible.
What's the estimate for the exchange?
Exchange energy.
For the exchange coupling.
Yes, I cannot tell you numbers, but you see it. Okay, you can see it here. So we are not fully quantized, and as you can see, it is flat. So the external magnetic field does essentially nothing. Okay, does it answer your question? Yeah. Okay.
But M versus H follows that loop, right?
Okay, I'll come back. M versus H. Yes, okay, so we don't have, that's true. No, this is obviously, so when we integrate our dipoles, it follows this perfectly. I don't have the data here, but we actually can integrate all the dipoles, and they follow this line. Exactly. Okay, so we have to keep in mind that these are actually very dilute semiconductors, magnetically doped semiconductors. And the question is why they become ferromagnetic. So one possible is, of course, you need some mediators. So one possibility is itinerant electrons. But by definition, we don't have any itinerant electrons if we are really in the quantum anomalous Hall state. The bulk is gapped, and the surface is gapped. So there is no reason for ferromagnetism in the first place. So the theoretical suggestion, is this Van Vleck mechanism, which actually mixes deep levels in the conduction band with the valence band. But it's still an open question, what is the source? We also have to keep in mind that everything is quite inhomogeneous, as is known from STM and other studies. So if we again think of electron puddles, then the size of these electron puddles should be very sensitive to the Fermi energy. So now what we can do next is to change the backgate and see what happens to this ferromagnetic structure. So if you look at global transition, so these are for the different backgates. And again, added to your question, you see they're all flat. So external magnetic field is not an issue. And what you see is, so this is for different backgates. And you see that essentially the coercive field is backgate independent, or independent of the carrier concentration. So so on macroscopic scale, changing carrier concentration doesn't do anything to the magnetism. So they are completely decoupled in this sense. But one can do a more careful study. And so here you see a large hysteresis as a function of the magnetic field. But what actually drives the system is the magnetization and not the external magnetic field. So in order to avoid this, we can plot Rxx versus Rxy. So these are exactly the same data, just replotted in a different way. And you see these arcs. So these arcs are actually, for each gate, you have a separate arc. And you can see, for example, that Rxy goes from negative value to positive value. So this is going through this plateau transition where Rxx peaks and goes down. So Rxx peaks and goes down. So this is the arc. And essentially, the plateau values are just the endpoints of these arcs. So actually, most of the data here is what happens in the transition. So this gives us a very easy handle to separate the two systems. So a backgate, namely carrier concentration, moves you vertically or along this diagonal, let's say, from one arc to the other, whereas magnetization takes you along the arcs. So for example, if you prepare our system, let's say at this point is here. And now let's do time relaxation. So this is what happens when we just wait. The movie that I showed you, that we wait for 20 minutes, what happens is that we're at constant field, just the magnetization goes down, so we move along this vertical line. This is real data. And here on this plot, we follow this arc. So following this arc maps out the magnetization. Now we can change the backgate, which should take us from this arc to this arc without moving along the arc. So what we do here now is just with very small adiabatic excursions of the backgate of plus minus 3 volts. So we start with small, and we increase them. We should have, what we would expect is to go back and forth, let's say, between these two things. But actually, we go back and forth, but also we slide down along this arc, namely that the magnetization relaxes much faster when we start changing the gate, and we see it in the images. So this time took about I don't remember, an hour, right? This was about an hour, but this, in a few minutes, we can get much larger relaxation. And this, we can take it to extreme if we do gate excursions of plus minus 30 volts very slowly on a scale of minutes. we actually collapse the magnetization completely, as you can see here. So let me just summarize the observations. So first of all, instead of seeing a ferromagnetism, which we expect, so the main idea is that we have to have a long-range ferromagnetic order in order to break the time reversal symmetry, in order to establish a macroscopic quantum state. This is not what we see. The system is highly non-uniform, and it's very surprising how come such a disordered system shows a macroscopic quantum state. So what we see is that we see isolated nanoscale magnetic islands that behave like superparamagnets. There's no long-range magnetic order. There are no domain walls. There's no dynamics of domain walls like in a ferromagnet. And we see thermal activation, namely these superparamagnetic islands that are slightly below their blocking temperature. The dynamics is very slow. We see that the magnetic and electronic systems are coupled. So obviously, there is a very strong coupling between the magnetic system and the electronic system, which drives the Plateau transition. The changing carrier concentration does not change global properties, but actually locally, it strongly enhances the magnetic relaxation. So if you think of these islands, so somehow by changing the carrier concentration, we don't change them significantly, but somehow we change interaction between them. That's how we think about it, and then we help them, because you are in a tilted potential, so any distortion will pull you down the hill. And then the big question is, how come we have quantum anomalous Hall state in absence of this long-range ferromagnetic order? And very well, it could be the reason to why the quantum anomalous Hall state is so fragile. Why do you have to go to dilution-free temperatures while all the other energy scales are orders of magnitude larger? And I was very happy to hear in Professor Hugh talk that now actually you can get to almost a Kelvin to still see quantization. So it might be very well that the ferromagnetism is the source of this very fragile state. Thank you. We can turn on the lights now.
So I just was curious what is known, or even just to speculate. So if I just had the ferromagnet by itself, there would be some domain wall energy.
Right.
And if I now have this edge state, and I could think about...
Edge state or surface state?
Well, the edge state between the ferromagnetic domain.
Yes. What
I was kind of curious about is the electronic edge state a large or small fraction of the total energy as compared to a naive magnetic domain? I mean, does that shift some of the balance of stability here?
Let me understand your question. Do you ask whether we have an estimate of the domain wall energy?
Yeah, but so the domain wall energy, we know what to think about for just the magnetic system.
Right.
But in the presence of this edge state that's topologically required, is that a big or small energy compared to that kind of canonical domain wall energy?
I understand your question. So two answers. First, I don't know the number. Second, we don't see any domain walls. So we see isolated islands that don't touch each other, essentially. And there is no domain, so there is, you may call it domain wall, but in a sense that they are, like you would take magnetic nanoparticles, powder, put them next to each other, so you can call the vacuum between them as domain wall. But they behave as independent particles, flipping each other, not talking. So when they flip, there's no correlation between them. So if it would be a macroscopic domain wall, you would see propagation. Let's say you have strong pinning of your domain wall, and your domain wall is rough. Then they would go by jumps, but you would see a correlated motion, right? All these guys are flipped, and this is not what we see. So these are sort of particles that each of them has a different coercive field, and they flip regardless of each other. This is very similar to what, by the way, completely different systems that we've seen, what Yoni showed this morning in the LMO STO. There it's in-plane magnetization. This is out-of-plane magnetization.
So what's the anisotropy energy? So this is unusual to have a ferromagnetic
yes.
where the magnetization likes to be so strongly out of
plane. That's a good question.
From of the anisotropy energy?
No, I don't know. Maybe you have the answer. Do you know what's the anisotropy energy, Lauren?
I don't have a number, but if you go to this Van Vleck mechanism that actually is Bloomberg or Rollins, as most of the old-timers call it, you will find that the selection rules are such that ionization should go perpendicular. So that's a strong argument that you can have that type of interaction in these systems. And this is not open-dependent. So it's really not how they do that.
That comes from the
Another
business.
thing to mention, I think, is that these systems show the scaling that people predicted for the quantum Hall effect, say, in the late 80s, which we never found. For me, it looks as if what you get in these samples, you have all these little microcrystallites, that's basically what's happening, and these are not pure single crystals, these energy. So you have all these little microcrystallites, and some of them can percolate, and then form a channel going over the sample. Many of them simply don't participate.
We think it has to do with the inhomogeneity of the manganese. By the way, we looked at chromium-doped, manganese-doped, and vanadium-doped from different groups. All of them look the same. Yeah.
Back to my earlier question, how do these results depend on the concentration of the dopant? Could you have these domains merge as you increase the concentration?
Okay, so a good question. So we didn't do anything systematic, but we tried to get from collaborators best samples that are as close to quantization, and there you need to do fine-tuning. But we also looked at samples that are very far from quantization, they never show quantization, and qualitatively they look the same. The size of the domains might change a little bit, but so this magnetic structure looks very similar in samples that are essentially show quantum Hall, anomalous quantum Hall, and those that don't. Adi? Yeah.
You have very large OXX, right?
Yes, so we have, yes.
Together with very nice, with almost precise quantization. Do you understand this?
Well, ρxx is always much more sensitive to being away from quantization than ρxy. So you in order to get ρxx to few ohms, which is in the best samples, you have to get your ρxy to, I don't know, 99.9%. So when you go away from let's say, when you tune your Fermi energy, so the ρxx deviates much earlier before ρxy deviates from quantization. Okay, so this is a 250 millikelvin. So all these samples, you have to cool them to below 50 millikelvin in order for the... I don't have a slide here, but even at this temperature, we see a dip in the ρxx at the right gate. But it doesn't go all the way to 0. Okay, at this temperature. You have to go to lower temperature. But the magnetic structure, the characteristic temperature scale is many kelvins, so this is not affected.
Okay, we'll move on to the next talk.